So I wanted to give a little bit of the backstory about what's going on with invariant subspaces, because this will be helpful for when you look at problem number 16 in section 6b. So here's sort of an explanation by way of example. So suppose we've got some vector space and it's the direct sum of u1 and u2 and u3. And each of these is an invariant subspace under T. And so just to make things concrete, I'm going to take the first one to be the span of E1 and E2, the second one to be the span of these other three vectors, and the third one is just going to be like a one-dimensional guy. Okay, and so note here that these like E1, E2, E6, this is not necessarily an orthonormal basis. And I'm not assuming from the outset that these are necessarily eigenvectors. Some of them might be, like E6 is going to be an eigenvector, but they're not all required to be eigenvectors. I'm not taking any fancy basis here. Okay, so let's see. So if we write A in the matrix of this basis, so the basis just chosen so that it's it's got the three invariant pieces for T, and A is the matrix of T, then it's going to have this sort of block diagonal shape. So there'll be stuff corresponding to E1 and stuff corresponding to E2 and stuff corresponding to E3 coming down the diagonal. Everything off the diagonal will be 0. These are all blocks of zeros out here. So that when you do the multiplication, the product of this row with this column, well, these zeros are going to kill anything that's showing up out down here, so it doesn't even matter. So it's going to take stuff from, and then this is what's spanning a U1, right? It's going to take stuff from U1 and spit them back into U1. So there's the invariance happening right there. So if there was, say, some non-zero term in this one right here, then when I do the product of this times this, it's going to pick up data from these two and inject it into here. Okay, so then that would be a situation where U1 is not invariant because vectors from U1 are getting launched to some place down here which is not inside U1. Okay. Yeah, and then similarly, so if we look at the next block, we have the same kind of thing. When I do this, oops, let me change the highlighter, there we go. This product right here, what happens is the zeros from this part are going to kill all the non-zero entries. And so you're just going to end up with zeros here and here as well. The only way you can get non-zero stuff is by taking something where the non-zero items match up in the multiplication with the non-zero items over here. That can get you a non-zero item in the product. Okay, so this is sort of the matrix picture behind these invariant subspaces. Okay, so now what happens with those things? Are they eigenspaces or not? Well, not necessarily. So suppose here that we have T of x, y, and then the other four terms is given by y0 and then something having to do with the other four terms, right? So I'm just looking right now at this first block here. Then then that block, so that 2 by 2 ends up looking like 0, 1, 0, 0. And so this is a strictly upper triangular matrix. And so we see that U1 is in the null space then of T squared. Because after I apply T twice, it's going to kill anything that lives in that first invariant subspace. And so another way of communicating this same idea is that if I look at T restricted to U1 and I raise it to the power 2, I get 0. So this is an example of an operator that we say is nilpotent. Potent meaning power, and nil meaning 0. So in other words, if you raise it to a power, you get 0. So now suppose we have v1. Let's say, well, if we look at v1 being 0, or sorry, 1, 0, and then like whatever stuff, say zeros. Yeah, I guess these are all going to be zeros. This is an eigenvector for our eigenvalue 0, right? It is the only eigenvector of this matrix. So this 2 by 2. So it is not diagonalizable. Diagonalizable. There we go. Okay. Now if I take v2 to be 0, 1, 0 like this is not an eigenvector, but tv2, which is equal to v1, is an eigenvector. So what's happening here? Well, we're in a situation, this crazy nilpotent thing is moving a non-eigenvector into an eigenspace. So you have this invariant subspace and it's kind of churning around, and stuff that's not eigen is being made into stuff that is eigen. And so you can ask yourself, like, okay, so how long can this kind of thing go on for? And so it turns out it can go on for a while, but it's always a finite number of steps. So suppose now we look at the next block in the decomposition here, and suppose we define the operator on this one so that well, it does whatever to the first two, I don't care, but then it does the same sort of shifty business to the those three that correspond to this invariant subspace. So you can see this is going to map the subspace spanned by E3, E4, E5 back into E3, E4, E5. But now the corresponding matrix, the 3 by 3 block matrix on the diagonal there, now it looks like it's got a 1 there and a 1 there, and everywhere else is a 0. Okay. And we have that U2 is in the null space of T cubed. Or, putting it in the other terms again, if we look T restricted to U2 and cube it, we get 0. So it's also a nilpotent. Alright, and so then we have W1, so this might be 0, 0, 1, 0, 0, 0. So that's an eigenvector for lambda equals 0. But there is no other eigenvector. If we look at W2, it's not an eigenvector, but T of W2, which is W1, is an eigenvector. And we can back this one up another step and say, okay, what about this one? This one also is not an eigenvector, but T squared applied to W cubed gives us W1 again, so that, oops, that one is. So you get the idea here. Now, all the stuff that I've been talking about right here, this is just for the eigenvalue 0 because that's the simplest case to write down, and it keeps the arithmetic nice and tidy for what's going on. But the general idea is something like this, right? So you might have some three-dimensional eigenspace, and when you so here's like the unit cube in this eigenspace or something, and then when you apply the t to it, then stuff, this box might get scrunched somehow into this to some parallelogram over here in the plane spanned by just these two vectors right here, and then you might apply it again, and it might get smudged into some some interval just on that bottom line, and then after that it gets dead. So something like that. So that's how these nilpotent operators work, sort of geometrically. Takes a three-dimensional thing, collapses it into a two-dimensional thing, which collapses it into a one-dimensional thing, and each time it sort of moves like to a different, like it moves around in that space. Okay. And there's probably some shearing going on. Okay. So, yeah, maybe that's a good little picture to draw, actually. So if I have actually, forget the matrix, but if I have a shear, it's the kind of thing that takes a square and maps it into a parallelogram like that. And so if you imagine doing this backward, suppose that this is an eigenspace here. Whoops, that this axis is an eigenspace. Then when I do the shear, this vector right here might land boink on that axis, and then it would become an eigenvector after having one application of the operator. Okay, and so the last thing is that there are other possibilities, but they basically come by subdividing these ones we already looked at. And so this is a topic for the latter part of chapter 8, actually. But you can have, like, what if this 3x3 grid of stars actually broke down kind of like this one? Well, so now what are we going to get? We're going to see that this guy right here is going to correspond to an eigenvector, because it's getting it's going to be mapping back into that same part. And in fact, we fracture this dimension 3 invariant subspace into two parts right here, where this one, this purple one, corresponds to an eigenvector, and this part up here is going to be a nilpotent of order 2. So that kind of thing can happen as well. But, all right, that's basically the whole story.